Hello everybody, I'm going to record a video now on multiple regression with interaction effects. I think this is quite an important topic. It will come back quite a lot when we talk about factorial design ANOVA and mixed design ANOVA, which are two things that are used a lot in psychological research. So please try to follow along the example here, try to pause if you need to. If you have any questions, feel free to reach out to me as well for clarification. So let's say we measure a outcome variable or dependent variable. Let's say we measure happiness. We can call it H. We can also call it Y because it's an outcome variable, but I'll call it H for now. And suppose we measure this in two groups. We have hamsters and cats. Let's draw the hamsters in blue. Suppose I measure a 2.5, a 4, and a 2.5. And for the cats, suppose that I measure a 1, a 1.5, and a 3.5. These three measures belong to cats, and these three measures belong to hamsters. Now I want to predict this from a predictor or X variable. Let's say we call that loneliness or L. There. Okay, so suppose that I measure the following loneliness: 5, a 3, and a 1 for the hamsters, and for the cats, a 3, a 4, and a 2. All right, so let's say both are measured on a 5-point scale. Maybe an average over multiple items that are measured on 5-point scale. It doesn't matter that much. So let's see what this looks like. Let's draw a graph here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let's say this is our predictor, loneliness, and this is our outcome variable, happiness. We have 0, 1, 2, 3, 4, 5, and 0, 1, 2, 3, 4, and 5. Okay, so let's draw our data in this scatter plot. So the first observation had a loneliness score of 5 and happiness of 2.5. That would be here, about there. The second observation had a loneliness score of 3 and a happiness score of 4. That would be here. And the third observation had a loneliness score of 1 and a happiness of, again, 2.5. Here. Then for the cats, we saw that the fourth observation, or the first cat, had a happiness score of 1 and a loneliness of 3. That would be here. The second one had a loneliness of 4 and a happiness of 1.5. That would be here. And the third one had a loneliness of 2 and a happiness of 3.5, which would be here. All right, so now we can do a simple linear regression model. Simple meaning we only have one predictor, where we try to explain happiness from loneliness. So let's say we have our model, happiness. The predicted value of happiness, so I'll just talk about the height of the line, equals some intercept. I draw the hat here to show it's an estimated value. If you don't draw the hat, it's the population value, which you don't know, that you have hypothesis about, plus B1 hat times loneliness. Now, if I did not include this hat here, I could have added an error term. Right now, to keep things simple, so I don't talk about the error here. All right. If you would do this in JASP, for example, you can fill in the data and you can estimate the parameters. That uses something called ordinary least squares estimation, which basically means it tries to fit a line as best as it can. Now you don't need to know how those parameters are estimated, but Jazz will return them for you. So in this case, we would get as intercept um, 3.1 and a slope minus 0.2. Okay, so what would that look like? We would have an intercept here, let's say 3.1 would probably be somewhere around here. And it goes down 0.2 for every 1 unit increase. So 5 times 0.2 would be a 1 unit decrease. Oh, let's draw more from here. There it is 1.1. Would go down about 1 unit like this. So that would be roughly our best fitting regression line. But now, let's suppose we want to take group membership into account in the analysis. So for example, we're actually interested in comparing the hamsters and the cats, or we want to see if the effect between loneliness and happiness goes away if we control for that we have different groups. So let's get rid of our line here. And also let's get rid of these values here. Because we're going to estimate a different model, so you get different parameter values. So now let's say add, I need to add the data first, a group membership. And I'll just call this, I'll just code this as 0, let's put it in blue, 0 for the hamsters, and 1 for the cats. Now I can form a multiple regression model where I add a second parameter times the group membership of the data point. Now the moment you add a second parameter or a second predictor, in this case, you're no longer actually fitting a line. You're fitting a surface in three-dimensional space. You can see it like that. But since here the predictor is only 0 or 1, for each of those values, we can still see it as a line, which makes it a bit easier because we can make a more easier picture here. So if we run this model in JASP, we would get our estimates for all 3 coefficients. And in this case, what we would get would be an intercept of 3.6, slope here of minus 0.2, and a group effect of minus 0.1. So what does that mean? If we try to draw the predicted line, for the hamsters, this group is 0. So for the hamsters, it's easy because we just get rid of this term to draw our line because this is 0. Let's not do that. So that means that for the hamsters, we just need these 2 parameters to draw our line. We have an intercept of 3.6, let's say about here, and a slope of minus 0.2. So that would be, I'm going to guess about this. Seems about right? Seems about equally from the blue points. Then for the cats, we add this term because this is now 1, right? So for the cats, the expression is B0 plus B2, and you can see that as a different intercept plus B1 times loneliness. because this G here is 1 for every cat. So let's clean this up a bit. So that means that for the cats we use all 3 coefficients, and we can see that the intercept basically goes up or goes down with -1 point. Okay, so let's try to fill it in. When the loneliness is 0 in the model for the cats, we get 3.6 plus, well, this is 0, so that doesn't matter. So 3.6 plus -1, so -1 times 1, we get 2.6. That would be about here. And then for every 1 unit increase in loneliness is just this one parameter here, -0.2. So we get 2.6, and a line goes like this. So what can we see now? We now have 2 lines, right? One that's different for the first group compared to the second group. And what do these parameters tell me? Well, we don't know if they're significant, right? We should test that, probably with this sample size. They're not, but let's just assume that they are significant. It tells me that on average, with a 1 unit increase in loneliness, happiness goes down with 0.2 point. And it also tells me that the cats on average score 1 point lower than the hamsters, because this line of the cat is lower than the line of the hamsters. Now, one thing you can see is that the shape of the line is still the same. You just move it up or down. But we might want to fit a different line for the cats and for the hamsters. And this is where the interaction effect will start playing a role. Let's remove the lines here that we added, and let's remove these values here. I'll use my eraser for that. And now I want to add an interaction term to this model. And the interaction term, I'll call it I, is quite simple. It is the loneliness times the group. So that means we multiply 2 values with each other to get this value. So in this case, 5 times 0 equals 0. So I draw here a 0. In this case, 3 times 0 is 0. And we can see actually that all these values for the hamsters will become 0. Now, for the cats, it will be different because we're doing this times that. So it's 3 times 1 equals 3. So what we see, the values for the cats become 3, 4 times 1, 4, and 2 times 1, 2. So now we have a third predictor, I, or the interaction effect, which is actually just the 2 values, the 2 variables multiplied with each other. So we can add that in the model. I add a third parameter times this interaction effect. And then what will happen is I will get also a third estimate. Now, these again will be different from what we estimated before, because it is a different model. There's different parameters, so you'll get something different. In this case, what happens is if you run this in JASP, we would get the estimates, intercept of 3. Now this slope would be 0. We get a beta 2 of, or B2 of 2. And finally an interaction effect of 1. B3 would be -1, sorry, -1. B2 would be 2, B1 would be 0 and B0 would be 3. So what does this mean? So we can see that if you have hamsters, again, these are a lot of zeros, right? A lot of zeros. So this model is relatively simple. Anytime we see G or the interaction effects, it just drops out. Right, so B2 and B3 are not playing any role for the hamsters. So that means we just need these two values to draw the regression line for the hamsters. Okay. So let's look. There's an intercept of 3 and a slope of 0, meaning that we now have a flat line. And you see that fits really nicely through the blue points. Right? So this line only cares about the blue points, not about the purple ones. Now, for the purple line, we can see that then this is 1, and the interaction effect is actually then the same as the loneliness variable, because this is the same. So we can see that again as a linear regression model. We have as intercept now B0 hat plus B2 hat. That's because this is just 1 always. Plus, and a slope, we now have B1 hat plus B3 hat. And that's because this thing is just the same as L. Now that's very interesting, because it allows us to interpret these parameters. It tells us that this beta2, the B2 parameter, is the difference in intercepts between the two groups. And in this case, the B3 parameter, and that's because the way we encoded it, because we use 0 and 1, that might be a bit different if you use different encoding, but that will be concerned later. It's the difference in slopes between the two groups. And so in this case, we'll see that for the purple line, we will get a new intercept of 3 plus 2 equals 5, and a new slope of 0 minus 1 equals minus 1. We get an intercept of 5, a slope of minus 1, and we get this line. And we now see that this line really nicely fits through the purple points. And that's the idea of interaction. So we know now that if this B3, if that is not 0, we know that in that case there would be a different line for one group compared to the other. And we can see that as an interaction, but we can also see it as a moderation effect. Moderation means that the effect between two variables depends on a third variable. So in this case, the moderation would be, we have an effect of loneliness on happiness, but the group membership changes that relationship.